Welcome, senior network engineers and telecom professionals. You are entering a masterclass deep dive into one of the most critical and complex procedures in cellular access, the Random Access Channel, or RACH. We're going beyond the basics to master the advanced Layer 1 and Layer 2 mechanics of both LTE and 5G NR. RACH is the foundational handshake protocol. For any device, a UE, to begin communication, it must first align itself precisely with the base station, the E node B or G node B. This initial communication bridge is established exclusively through the RACH procedure. Fundamentally, RACH serves two core purposes: establishing uplink synchronization, ensuring the UE's transmissions arrive at the base station without time shift interference, and facilitating initial access to transition the device from a dormant state into active service. The random access procedure is not a single event. It is triggered by 7 distinct conditions defined by 3GPP. Think of them as 7 indicator lights on a master control panel. These include 1. Initial access from RRC idle. 2. RRC connection reestablishment after a radio link failure. 3. Handover into a new cell. 4. Downlink data arriving when the UE has lost uplink synchronization. 5. Uplink data arrival with no scheduling request resources available. 6. The critical 5G transition from RRC inactive state. And finally, 7. Requesting on-demand system information, or SI. Now, let's begin our advanced dive into the LTE RACH, focusing on the Layer 1 physical mechanics and the Layer 2 MAC control. This is where the physics and mathematics truly dictate network efficiency. The heart of the RACH preamble lies in the Zadoff-Chu, or ZC, sequences. These are constant amplitude zero autocorrelation sequences, a cornerstone of LTE orthogonality. The zero autocorrelation property is our key to extremely precise timing detection, like a perfect puzzle piece fitting into its slot. The low cross-correlation property minimizes interference when multiple UEs attempt access simultaneously, ensuring signals from different users don't completely clash. Each cell needs a set of orthogonal preambles. LTE provides 64 distinct preambles. These are not 64 unique ZC sequences. Instead, the E node B generates them from just one or a few ZC root sequences, designated by a root sequence index. The remaining preambles are generated by applying a specific cyclic shift to that root sequence. This elegant mathematical technique gives us the necessary isolation and ensures that a massive number of unique preambles are theoretically available across the network. LTE primarily relies on the 4-step contention-based RACH, or CBRA. Message 1, preamble. Message 2, RAR. Message 3, RRC connection request. And message 4, contention resolution. Contention-free RACH, or CFRA, is simpler, involving only message 0, a dedicated preamble signaled by the E node B, and message 2, RAR, bypassing the collision risk entirely. CFRA is reserved for time-critical, network-scheduled events, like handover. Layer 2 MAC controls the physics of the access attempt. Open-loop power control uses the downlink path loss estimate to set the initial transmission power. If message 2 is missed, power ramping dictates that the UE increases its transmission power step by step, like iteratively increasing the wattage on a light bulb, until the signal is received. For congestion, the backoff indicator, or BI, is used to introduce randomized delay to subsequent attempts. Remember the key timers. RA response window size dictates the listening period for message 2, and MAC contention resolution timer governs the wait time for message 4, which resolves the collision. Transitioning to 5G new radio, the fundamental process remains, but the context dramatically shifts due to beamforming, especially in millimeter wave spectrum. 5G RACH is inherently beam-centric. The question is no longer just, are you synchronized with the cell? But are you synchronized with the correct directional beam? In millimeter wave, coverage relies on narrow, focused beams. Before the UE can attempt RACH, it must first measure the received power of the synchronization signal blocks, or SSBs, transmitted by the G node B. The UE selects the strongest SSB. This chosen SSB directly informs the UE which PRAC occasion to use, essentially telling the G-Node B exactly which beam its preamble is coming from. The G-Node B schedules physical time-frequency resources called PRH occasions, or ROs. The mapping between SSBs and ROs can be configured dynamically. A one-to-one map provides high spatial granularity but increases overhead. N-to-one mapping means multiple SSBs share the same RO, which conserves resources but reintroduces contention. Conversely, 1-to-N mapping allocates multiple ROs per SSB, beneficial in high-traffic scenarios. This mapping is vital for the G-Node B to immediately know where to steer its uplink receiver array. 5G introduces flexible preamble formats. For lower bands, we use long preambles, similar to LTE. For higher, scalable frequencies, we use scalable short preambles, which allow for a flexible subcarrier spacing, adapting to different latency requirements. Furthermore, RACH in 5G is often restricted to a specific bandwidth part, or BWP, which is a key concept for energy saving and simplified UE complexity, ensuring the device only listens for RACH resources in a defined part of the carrier. 5G NR is constantly evolving, and recent 3GPP releases have radically improved the RACH procedure to support ultra-reliable low-latency communication, URLLC, and massive IoT use cases. Let's explore these advancements. Two-step RACH, defined as Type A, drastically reduces access latency. It merges message 1 and message 3 into a single transmission called message A, which includes both the preamble and the PUSH payload containing the initial RRC or small data message. The G-Node B responds with message B, which contains the random access response and the contention resolution. By having the messaging round trips, this is a game changer for latency-sensitive applications. Release 17 introduced Small Data Transmission, or SDT. This allows UEs in the RRC inactive state to send small bursts of data, typically less than a few hundred bytes, without executing a full state transition to RRC connected. This small data can be encapsulated either within the message A of a two-step procedure or within the message 3 of a four-step procedure, massively improving battery life and signaling efficiency for massive IoT. Finally, consider non-terrestrial networks like satellite communication, where propagation delays are measured in hundreds of milliseconds. Standard RACH relies on the G-Node B's timing advance correction. In NTN, the UE must pre-calculate its own timing advance using GNSS or GPS data before sending message 1, anticipating the massive delay. This pre-compensation is necessary to ensure the preamble arrives at the satellite base station at the exact scheduled time window. We have covered a significant amount of advanced material, from Zadoff-Chu sequences in LTE to beam-centric access in 5G NR. To consolidate this knowledge, let's compare the two architectures. LTE utilizes cell-wide coverage, while NR is highly beam-specific. LTE relies on fixed subcarrier spacing. NR introduces scalable SCS. LTE primarily uses four-step RACH, although CFRA exists. NR offers flexible two-step and four-step execution. And finally, LTE RACH occurs across the full carrier, whereas NR access can be restricted to a specific bandwidth part. These differences are key to understanding the performance and complexity trade-offs of each generation. In summary, LTE offers maturity and simplicity. 5G NR delivers ultra-low latency and beam efficiency, essential for future services. However, this comes at the cost of heavy beam management complexity and increased control overhead. Mastering the RACH procedure is mastering the foundation of modern cellular networks. Thank you for joining this masterclass. Stay connected, stay synchronized.